Welcome back, folks, to the very last set of videos for this course. We've come a long way. We've learned a lot. We've cried a lot. We've laughed a lot. I don't know. I sound like a bad mural on a wall. All right. This week we're gonna kind of tie up a couple more loose ends. Not really tie up some loose ends. I don't even know why I said that. What I mean is we're gonna talk about some other properties or some other things that could happen with our sets and with our vector spaces. Um, so this first thing, if you have taken Calc 3 before, or sometimes this comes up in physics, all kinds of things like that, you may have heard about a dot product. And so we use vectors often in applications in either in 3D spaces, in multivariable calculus, we talk about vectors. In in physics, we talk about vectors. So one of the ways you might have seen vectors talked about is work, where work is defined as the force times the distance. And especially if we're talking about work within a certain plane or work within a certain direction, one place you might see this is up an inclined plane. Right, so your force might be going this way, and we want to talk about, we have things like normal forces that are acting on this. There's the normal force that's keeping it that way, and then there's the force, the action force that's actually causing it to move. And so this is sort of a breakdown of things, and then we have however far the distance is that travels here, and that distance can be expressed as a vector as well. Or you might have maybe our pulling force is different and not along our plane of movement. Either way, this idea leads to what we call the dot product, or the inner product. Now, all this is just taking two matrices or two vectors and multiplying them. Now, of course, we've established that in order to multiply two vectors, or in order to multiply two matrices, we have to have that column row thing happening here. And if I tried to do this, right, this has 3 columns and 1 row, 3 columns and 1 row. Those are not the same there, which is a problem. But we can easily fix this by, instead of just taking U, we take its transpose. And if I take its transpose, all we're doing is vector multiplication. And we know that vector multiplication just says take the first row. So all this boils down to is that the dot product, U dot V, so U dotted with V, is defined by just taking the A1 position of U times the B1 position of V, right? So if this is A1, this is B1, plus A2, B2 times B2, right? And then the result here is a scalar. And that's all she wrote, right? So you can define it or redefine it by taking U transpose times V, or V transpose times U, depending on the order here. But it really doesn't matter. All we're doing is we're taking corresponding positions, multiplying them together, and then adding up those products there. So we'll multiply those things, right? And the nice thing about this, so if we go with our definition here, right, U transpose would be what happens if I take and I just flip this and it becomes horizontal instead of vertical. And then I'm able to multiply it by the 3 to -3. And as you can see, right, our matrix multiplication says first row, first column, or you kind of do the flip and the line up and the multiply, but it just comes out to be multiply the top two, the middle two, the bottom two, whatever. So we get 2 times 3 is 6, -5 times 2 is -10, -1 times -3 is a +3. Add those together and we get -1, okay? Now, if we go the other way, if we do V transpose times U, so V transpose is 3 to -3 times the 2, -5, -1. I'm hoping you're screaming at your computer right now and screaming, hey, those should be the same, which I darn rootin' tootin' they should be, right? Because you've got the same positions are being multiplied, whether we do u first and then v, or v first and then u, because of the way we're defining this particular brand of multiplication. All right, so it's not really multiplication in the sense that we would think about it as multiplication, which is why it has a different symbol. And the result is no longer a vector, but is a scalar. So here we'd have 3 times, why did I put -2? Oh boy, that was going to really mess with things, wasn't it? All right, so 3 times 2 is 6. 2 times -5 is -10. -3 times -1 is +3. Oh, hey, look at that. Hey, samesies. Yay. In fact, that is a property that the dot product of any two scalar or any two vectors, it does not matter the order that you go in, the dot product is commutative. Or it's commutative, right? Which it doesn't matter the order that we go in. The dot product is also associative, right? That's what this says, that if I take two vectors and I add them together and then I dot them with a third vector, it'd be the same as dotting individually those vectors with the third one and then adding them together. Same thing with this one's our scalar associativity, whatever, scalar stuff. And this last one is interesting. Right, so it says that u dotted with u is always going to be greater than or equal to 0. And if we think about that, that it sort of makes sense, right? So it doesn't matter. So let's, I don't know, let's even take the u that we already had, the 2, the -5, the -1, and 2, -5, -1. All right, we'll write it like this. And as you can see, it's always going to be, I'm going to have the 2 times 2, or the 2 squared. I'd have -5 squared, and I'd have -1 squared. And by the nature of squaring something, even if this is a negative value, this is always going to be a positive. Same thing here, this is always going to be a positive. So that's why if I take the dot product of a vector with itself, that result is always going to be a positive value, right? The only time that it's going to equal 0 is if our u equals the 0 vector, right? Because there's no way that I could get this to be a -4 if I wanted to get rid of this without right? Because I'm squaring it. And by the nature of squaring a negative number, we're always going to come up with a positive. So those are some of our theorems there about the dot product. It's sort of interchangeable whether it's called the inner product or the dot product. It doesn't really matter, but you'll hear dot product in other applications more often than you'll probably hear the inner product. Oh, okay. We were waiting there. So the next thing we want to talk about is the length of a vector. And this also has multiple names, but the length of a vector. So let's just, I don't know, I'm just going to pick some vectors. So let's let vector 1 be, I don't know, you ready for this? 3, 4. We'll let vector 2 be, I don't know, -1, -2, whatever. And just for funsies, just to really hammer this home and get an idea of what's happening here. I'm going to let vector 3 be defined by, ready? We're going to let vector 3 be equal to vector 2, vector 1 minus vector 2, just for fun. We're going to find the lengths of these. So that means that if I take vector 1 minus vector 2, 3 minus -1 is going to give me 4. 4 minus -2 is going to give me 6. So that's my vector 3 defined there. And so we'll make that one a blue one. I don't know, just for fun, we'll make that guy a green one, and we'll have vector 3 be a red one. So vector 1, 3, 4. Oh, hey, so there's vector 1. And I don't know if you know this or not, but oh, hey, look at that tiny little triangle there. And oh, I don't know, if I want this distance here, oh, that looks a lot like a hypotenuse, which is, part of the Pythagorean theorem. And, this height here, isn't that the y value of our vector? Isn't this 4? Right? That's the y component of our vector. This guy's here is 3. And, if you're tooting your horn about your Pythagorean theorem knowledge, hopefully you know that this is 5. So the length of vector 1 is 5, right? Because 3 squared plus 4 squared, square rooted, is 5. All right, does that always work? Can I always use the Pythagorean theorem? You betcha. All right, -1, -2. Here's this vector here. Okay. And, oh, look, hey, looks like, there we go, we got another triangle. This is a side of 1. This is a side of 2. And when we're talking about length, right, think about if you go to build something and you need to go cut down a board that's a certain length. It does not matter whether or not you measure it while it's standing up, right, so that it's like vertical. Doesn't matter if you have it cockeyed, if you have it somewhere else. The length of it is regardless of distance or regardless of direction, right? So length has nothing to do with direction. Same thing with like right? Length and distance are sort of can sometimes be synonymous. And it's always going to be positive. Right? So this is always going to be positive. Doesn't even matter. I mean, we could orient it in a different direction, but we're just talking about how long the thing is, so it doesn't matter whether it's pointing in this direction or in this direction, somewhere over here. This vector flipped around, so the negative of vector 1 is still going to have the same length as vector 1. Because all we've done is flipped it around and it's just going in a different direction, but the distance, or if I measured from here to here, is always going to be the same. Hopefully that makes sense. So this one here, the length of V2 happens to be the square root of 2 squared plus 1 squared, which is square root of 5, right? And you can leave it as square root of 5. You can express it as a positive, express it as a negative, or not a positive. That's not what I meant. You could express it as a decimal. You could leave it as square root of 5, whatever floats your boat. I don't really care. But this is a whole, not a whole, but this is an exact value versus the decimal, which is probably something like, oh, I don't know, 2.7 something or other. Who knows? I don't happen to know my square roots off the top of my head. But that sounds right. Probably more like 2.2. I don't know. Yeah, your choice. All right, this one is going to be, and it will come up in just a minute again, this idea of the subtraction. But the vector 4, 6, so 4, 1, 2, 3, 4, 5, 6, this vector here. If I notice this guy here, if I take him, if I take this vector and I move it, do you see what happens here? So this here is just this guy moved up here. And so turns out that, and if I flipped that guy around and, whatever. Basically, we've created a lovely, just go with it. All right, we're just going to roll with it. All right, so our V3, the length of V3 is just our square root of 4 squared plus 6 squared. So what is that? 16 plus 36, which is 454, square root of 54, which I could probably do something with to simplify it, but I don't care. Square root of 54. There you go. Ta-da. Now, we have special names for the length. So in linear algebra, it often gets called the norm. And in Calc 3 or in anything involving physics, you'll often hear it as the magnitude. Those mean the exact same thing. Now, often when we talk about the norm, we use these symbols where you see this. It kind of looks like a double absolute value sign, but it's not the absolute value. For magnitude, we'll often use just a single looking absolute value, and it means the same thing. It's just different branches of mathematics adapt different symbols in different ways. So magnitude, it'll often look like the absolute value, and that kind of leads to the idea that it's the that it's the length, right? Length is always positive, so if you think about absolute value always being positive, that's kind of an homage to that, I guess. But the norm, one way to define it is the square root of the vector dotted with itself, right? Which is the same thing as up here, right? When I use the Pythagorean theorem, the vector, the components that make up the vector, are the things that make up the sides of that right triangle. And this happens no matter what base we happen to be in, or what dimension we happen to be in. If we're in R2 like this, it's pretty easy to see that triangle. In R3, you can even make a triangle that way, and it works out the same way. But it's always going to come down to, if you take the square of each of the components, add them together, and then square root it, that is your magnitude. And hopefully it makes sense that if I take the magnitude of something and I square it, it's equal to what I would get if I dotted the matrix with itself, right? So let's take V1, for example. So we found, so V1 dotted with V1 would be 3 squared plus 4 squared, which is 9 plus 16, which is 25. The magnitude of V1 we found to be 5, so 5 squared is 25. Hey, look at that. Hopefully that makes sense too. All right, last one we're going to define, and then we'll do some unitizing here, is a unit vector. Now, a unit vector is a vector whose length is 1. And to get a vector, so to take any vector and make it a length of 1, all we need to do is divide by its length, right? So think about, if my length is 5 and I want to get it to 1, 5 divided by 5 is 1, right? So all we need to do is divide the whole vector. So we're multiplying by a scalar, but that scalar happens to be a fraction. So first thing we need to do is find the magnitude here of v. So we're going to find the magnitude of v. And I'm going to actually let you pause the video and come back to this and decide what the magnitude is for yourself. All right, pause, come back. All right, so I found that the length of this vector is 3, or the magnitude or the norm, whatever you want to call it, I don't care, is 3, right? Because 1 squared is 1, 2 squared is 4, so we're up to 5 plus another 4 gives us to 9. Square root of that is 3. So all we're going to do is take all the components in this vector and multiply by 1/3. So our unit vector for v, I'm going to call it u. And if you want to, you could, sort of relate it back to, you could put a little subscript v there so you know that it's the unit vector for v. However you want to name this, don't matter to me. But our unit vector is just each of those components divided by 3. So it would be 1/3, negative 2/3, 2/3, and 0. And if we really wanted to test that this actually does give us a magnitude of 1, we can take or a length of 1, we can take and find its length. So to be 1/3 squared plus negative 2/3 squared. Now I don't have to worry about the 0, right? Because 0 squared 0 times anything is 0, and adding it to is not going to change anything. So So this will give us 1/9 plus 4/9 plus 4/9. 1, 2, 4 plus 4 is 8 plus 1 is 9. So this is the square root of 9/9, which is 1. Ta-da! So hey, it works the way we would expect it to. All right, this next question, and this notation is a little bit different. So you'll notice that this vector here is not actually in our traditional vector form. Instead, it's listed as an ordered pair, all this means is if we're going to translate this into vector form, this says that our x, oh goodness, colors, Jesus. This says that our x vector is just the vector 2/3 1. That's all it is. So we want to find a unit vector z that is a basis for w. So w is this set spanned by this line here, or by this vector. So if I take 2/3, I don't know, we'll make that be 1. So I don't know, 2/3 is roughly there-ish. So there's 1. So 2/3, 1. So what they're telling us is that our w is this line right here, right? Because if I span a single vector, the span of x is the line through the point 2/3, 1. That's all it is, right? That's what w is. So this represents w. And what we want to do is, this is technically, so this here, because we're talking about w representing a line, this here is a basis for w. What we're asked for is a unit vector z that is also a basis for w. Right, so we're not going to combine these two ideas together. We're just going to find a unit vector for this. So the first thing we need to do, again, is find the length of x, which means finding some, so 2/3 squared plus 1 squared, going to give us 4/9 plus 9/9 is a whopping 13/9, which is square root of 13 over 3, which is not beautiful, but who cares? So this is my magnitude, or that's my length, which means I'm going to take my x vector and I'm going to divide by that. So my z vector is defined by taking my x vector divided by the length of my x vector. And this division, again, it's division, and it's possible to do division in this case because this is a scalar. And all this means is that we're doing scalar multiplication. Now, it's scalar multiplication of a fraction, but that's okay. So all I'm going to do, I'm going to take and I'm going to flip this because I'm dividing by a fraction. So this means I'm going to multiply by 3 over square root of 13 times my 2/3 vector and my 1. And this will give me 2 square root of 13 over 13. I'm rationalizing my denominator here. And then 3 square root of 13 over 13. Right. Hopefully you followed my steps there. I multiplied this, and then I multiplied the numerator and the denominator of each fraction by square root of 13 over square root of 13. Or I could rationalize this one first. We're on a little side trip here about rationalizing denominators. 3 over square root of 13, if I want to get rid of that 13 in the denominator, I'm going to multiply by square root of 13 on the top and the bottom. On the bottom, a square root times the square root of itself just gives you the itself. So this becomes 3 square root of 13 over 13. And you could also do that in this process as well. So whatever, makes you happy. Float your boat, get you there. All right, that's a lot about unit vectors.